So our next speaker is Robbie Wilson from NASA Goddard, and he has a very long title, so I'm not going to going to read it out.
Okay, can people hear me online, through the microphone, everywhere? Okay. Excellent. Check the pointer. That's very cool. All right. So the idea with this talk is I wanted to give a very sort of broad breadth overview of a few different problems that we'll be able to solve using the transiting planet sample and do mostly largely to just the sheer sample size that we have that we just didn't have from any other previous mission. So for a quick difference, so people can kind of understand what's going to change from. Okay, thanks for turning that on. It's a good idea. Yeah, so when we're talking about transit sensitivity, right, we're sensitive to very close-in planets, and we're sensitive to larger planets. So to bring this curve down to smaller planet radii, which I've converted to planet mass using a mass-radius relationship, just so we can compare to microlensing, you would need better photometric precision or smaller stars. And to push to larger semi-major axis, you need some combination of more stars so that you can overcome transit probabilities at large separations, or you need really, really long baselines to get, so that you can observe more transits, Phillips signal noise. So most of what I'll be talking about are these very close in, within about a third of an AU. But we are, if you compare to microlensing, for a Jupiter-like planet, a Saturn-like planet, we actually have very comparable sensitivity from getting single transit events. So we will have a pretty broad sample to work with, but nowhere near small enough to probe the kinds of questions that Eve was discussing. Right, so what's the total? So the total yield should be around 10 to the 5 planets from this sort of estimate at the top, which is a very simplified version of what we did in a much more complicated way with pixel level simulations, measuring the noise, et cetera. I didn't want to, but we can kind of skip over this part and just go straight into the theory. And so I think that we have one big issue that we need to overcome, which is that follow-up is going to be very difficult. These are all really dim. And so I think the best way to approach this is to think of this as an almost purely demographic sample, right? So we're not fitting individual planets, we're fitting distributions. And the nature of those distributions is going to depend on the false positive rate, it's going to depend on the galaxy, it's going to depend on many, many things. But with that in mind, I want to introduce my science philosophy for this project. So this is a quote from late 19th century journalist. When nothing seems to help, I go and look at a stonecutter hammering away at his rock, perhaps 100 times without as much as a crack showing. Yet at the 101st, it'll split in two. And I know that that was all because of the previous 100 blows, not the one before it. If you're a basketball fan, you might recognize this as the training mantra of the San Antonio Spurs. And my response to this would be, we should just get 101 hammers. And then maybe you only have to swing once. So a few of the rocks we can smash using this sample. So giant planets hosted by M dwarfs. So this is sort of complicated so this is sort of an issue for planet formation. And so we can we're going to bring some hammers to smash the rock. And so the main issue is, sort of in a very broad way, that there's just not enough dust to form some of these planets. It doesn't really make sense to form them through core accretion unless either the disk has a lot more dust than we realize, planet formation is more efficient than we realize, or there's some other mechanism that they're forming, such as gravitational instability. Right, and so this plot over here on the right is showing in orange the distribution of dust mass for protostars. And then the green points are the amount of heavy material that's inside of several giant planets that have been found by tests. And so at the current moment, we have about a sample of 30 giant planets with M-dwarf hosts, which is quite nice. But with Roman, we'll have significantly more, and we can test some things, not by measuring their masses because of this problem here. It's going to be really hard to get radial velocities for these stars. They're going to be 21st magnitude, roughly, or 20 to 22. But we can measure their dependence on metallicity, again, not spectroscopically, not through not through spectroscopy, but by using the galaxy. So there's a metallicity gradient in the galaxy in the thin disk. Roman's probing a significant part of that. And so we can leverage this difference to see how the occurrence rate of M-dwarf giant planets changes as a function of distance. And so there's a lot of spread in the metallicity, but we have a really large sample and we can marginalize over a lot of it. And so this is some results of our simulations that we've done. And in particular, planet yield is a function of distance. In particular, the middle panel is what I want to point out. The top row is showing what you would expect given a Kepler-like occurrence rate. The bottom row is if you account for that metallicity gradient in the galaxy. And pointing specifically to M-dwarfs, you see there's a huge bump at about 4 or 5 kiloparsecs, and this would extend further. And the size of this trend is about an order of magnitude. So we have a very strong prediction that could tell us whether core accretion is a viable mechanism for these systems. And by viable, I really mean common. And so those are the hammers we have for this problem. So another problem, tidal migration and stellar evolution-driven engulfment. So the first one was a problem that we're working on with planet formation. This is a problem we're working on in planet destruction, which by the nature is more fun. And so Roman will bring hammers. And so the basic idea is for a very close-in planet, as the star evolves, ascends the red giant branch, it's going to get larger and larger, and the stellar radius is going to become comparable to the orbital distance. And it's hard for planets to survive inside of giant stars. Not impossible, apparently, from some talks I learned not so long ago, but quite hard. And so you'd expect the planet to become engulfed, but actually this happens much sooner due to tidal forces that are not incredibly well constrained at the moment. So this is one idea. There's several of how this process could happen. But as the host star evolves around a large star, it creates these, or it excites these standing waves that propagate through the core of the star. As the star changes, that wave is no longer able to propagate. And that the wave instead heats up the core, steals momentum from the planet, and the planet falls into the star. Boom, boom. And so how would we test this? Yeah. Okay, so how we test this is finding stars or planets that are orbiting evolved stars. So in the sort of current landscape, especially close-in planets, there's of order 30-ish, 20, 30 sort of dozens. And with Roman, we're observing 2 million giants. And because of that sample size, we're expecting to find of order 2,000 giant planets orbiting giant stars. And depending on what you assume that cutoff to be, whether a star can orbit at the stellar radius, 3 stellar radii away, et cetera, that yield changes very dramatically, factors of 2 or 3. And so by looking at the orbital distribution for these kinds of planets, we can put very strong constraints on what tidal migration has to look like. And this is about, this kinds of planets where the giant stars will be looking at sort of 3 to 5 solar radii. All right, this is the last one. Also a different extreme. I tried to pick sort of 3 different theoretical areas for diversity. But we can start to constrain global climate models on hot Jupiters. And those are the hammers. So how can we do this? So one is through emission spectrophotometry. So we can measure the brightness temperature of the planet. That's hard to do when it's really close to the star, but we'll have a large sample that will have a secondary eclipse. So when the planet goes behind the star, you have flux only from the star and from the day side of the planet. So you can kind of see the diagram on the left, or right, stage left. And by measuring that difference, you get the brightness of the planet, or the day side of the planet. And if you look at this value and how it changes with equilibrium temperature, you can start to reveal some physics. So this is using a sample of about 120 Spitzer measured secondary eclipses. And you can see at about 1700 Kelvin equilibrium temperature, this trend changes. It's a very abrupt change. So the authors gave 2 reasons for this. So one is the onset of magnetic drag, which prohibits heat to be recirculated throughout the planet, or cloud dissipation. So at this temperature, clouds go away, revealing deeper, hotter layers into the planet. And so we can make similar plots, look at similar things, but we also have another tool, because we have so many planets, which is multicolor observations, which we can use to do transmission spectrophotometry. That's going to be very hard because these signals are quite small, order few hundred parts per million. And so we can average multiple light curves together and get a strong signal into the population. This is going to be difficult and relies on us correcting for a lot of systematics, but we're not limited by sample size and we're not limited by photometric precision, which are the 0th order things you need. And so that's what the hammer is for there. And what are we doing to try and do this? So we're doing simulations and we're developing infrastructure. So we've created some pixel and light curve level simulations. You'll notice from these we can create noise models. So this is the noise model on the right, the blue dots. The red line is Matthew Penny's 2019 noise model. And there's a very big discrepancy here. We've assumed that we can get good photometry in the edges of the PSF. And some people would call it optimistic. I would like to call it a goal. And we'll be helped by bright saturated star data that Josh talked about yesterday. And this effort is being led by Dana, Tom, and Josh. So we're hoping to incorporate this in there. And running a bit low on time, but more simulations. The choice of secondary filter, so we've looked at this a little bit. It's driven entirely by crowding and by extinction. So we can get really good photometric precision in the K band, which is the right column. And on the bluer side, we get much better results in the FO87 filter. We're developing a data-driven PRF light curve pipeline. So on the left is a simulated image. On the right is the PRF model we've developed from this. There's still work to be done. You can see that it's not quite capturing all the complexity of Roman. So this is ongoing work. But even as this, we're still getting precise light curves, if inaccurate. And then we're also doing other things. And yeah, so we'll find a lot of hammers. We're developing a lot of infrastructure. And preliminary lessons from simulations seem to indicate the 087 K-band filters will be good. And this is our team. Yeah. Thank you.
Thanks, Robbie. So we have time for one very quick question if anyone has it. Dan?
This will be an obvious question coming from me, but so for the red giant planet yields, for how many of those can you detect both the planet and do astroseismology? from the
Yeah.
order of 30,000?
It's a good question. Not many, I don't think. Maybe of order 3.
I was afraid that was going to be the answer.
Yeah.
Thanks.